Uh, Today with us is Dr. Rakesh Kumar Khare. Sir is my guide for both MTech and PhD. So now I request Professor Richa Jain to give a brief introduction of Khare sir.
Good afternoon, everyone. Now we have a second speaker of a day with us, Dr. Rakesh Khare sir. Sir is presently working as a professor in Civil Engineering and Applied Mechanics Department at SGSITS Indore. He is an expert in the field of structural and earthquake engineering. Sir has completed his BE in Civil Engineering and Master's degree in Structural Engineering from Bhopal University in 1985 and 1987 respectively. He has completed his doctorate degree in Civil Engineering in 1996 from DAVB University. His area of research interest includes finite element analysis and design of structures, financial seismic risk analysis of building and structures, nonlinear and incremental dynamic analysis of structures, seismic analysis and design of precast concrete building structures, computer-aided analysis and design of structures, static and dynamic analysis of fiber-reinforced composite laminated plates and shells, developed higher order facet shell elements, seismic hazard, and microzonation. Sir has supervised more than 9 doctorate theses and more than 90 MTech theses. Also published 40 papers, more than 40 papers in international and national journals in reputed journals. Also, he has successfully accomplished various projects of DST, MPCST, and other funding agencies. Sir is a member of editorial board for review of research paper in Indian Concrete Journal, Journal of Composite Structures, Journal of Sound and Vibrations, Structural Engineering and Mechanics, Mechanical Sciences, and many more. Sir has been awarded with various titles as INAE Fellowship, also awarded Best Supervisor for MTech Thesis, received NPEEE Fellowship, and received Fellowship for In-Service Young Scientists twice. Sir is a member of various professional societies like Earthquake Engineering Research Institute, USA, American Society of Civil Engineering, Indian Association of Computational Mechanics, Institute of Engineers, Indian Geotechnical Society, Indian Society for Technical Education, Indian Water Resource Society, Association of Structural Engineering, Indore. Now I welcome Khare sir for his lecture.
Thank you.
Thank you, sir.
Can I start my presentation?
Yes.
Okay. So this lecture is on the introduction on IS 1893 2016 and IS 13920 2016. These two standards are basically for earthquake resistant design of structures and ductile detailing design of RCC structures. Different codes. So IS 1893, second slide. Criteria for earthquake design of structures is IS 1893 2016. There is one more code, IS 4326 1976, that is Code of Practice for Earthquake Resistant Design and Construction of Buildings. IS 13920 2016 is the Code of Practice for Ductile Detailing of Reinforced Concrete Structures subjected to seismic forces. And there is one SP22, that is Explanatory Handbook on Codes for Earthquake Engineering. That is Explanatory Handbook for IS 1893. It is the old one. Explanatory Handbook of 2016 code is not yet available. So SP22 is Explanatory Handbook of earlier code, IS 1893. But you can do this in presentation mode, I think that would be better. Slides. F5 or something.
Yes, sir. Should I stick with this, sir? Skip.
No, not escape.
Yes.
You can present in this complete presentation mode. Slide
Sir,
show.
yeah, okay, sir.
If it is not possible, it's okay. Otherwise, the slide show
Yes, sir.
would be better.
Okay, sir. It is not coming, sir. Actually, I have done
Okay.
this also.
Okay. If people are comfortable, then it's okay. I think it's visible. Okay. So what is earthquake? Science. An earthquake is a sudden, rapid shaking of the earth caused by the release of strain energy stored in rocks. Various theories are there: tectonic plate theory and elastic rebound theories. So this presentation is not for the details of seismology. So I'll continue with the presentation. Next slide. What is the effect of earthquake? That is on this IS 1893 and 13920. Effect of earthquake: when an earthquake causes ground shaking, base of the building would move, but the roof would be at rest. Inertia forces can cause shearing of the structure, which can concentrate stresses on weak walls or joints in the structure, resulting in failure. Total collapse will not be there if it is designed properly as per as 1893. Definitely, total collapse will not occur. But of course, damage to the extent of near to collapse, severe damages may definitely occur if severe most earthquake is occurred. Next slide. So, since earthquake forces are random in nature and unpredictable, the static and dynamic analysis of the structure have become the primary concern of civil engineers. Main parameters on the seismic analysis of structures are load carrying capacity, ductility, stiffness, damping, and mass. IS 1893-2016 is used to carry out the seismic analysis of multi-story buildings. Earthquake resistant structures. Earthquake resistant or seismic structures are designed to protect buildings to some or greater extent from earthquakes. According to building codes, earthquake resistant structures are intended to withstand the largest earthquake of a certain probability that is likely to occur at their location. What is largest earthquake? Largest earthquake or maximum considered earthquake is the earthquake which have the probability of 2% in the design life of structure. So 2% probability in design life of structure has a return period of approximately 2475, so 25 something like that, 2500 years. And the one is design basis earthquake, which has 10% probability in the life of structures. 50-year design life of structure is there. Then that earthquake can occur in 475 years. That is, return period of the earthquake will be 475 years. So that is what the earthquake. So we consider maximum considered earthquake is in fact 2% probability in design life of structures, and design basis earthquake is 10% probability in design life of structure. Terminology of which are used in IS 1893. They are damping, the effect of internal friction in elasticity of material, slipping, sliding, etc., and reducing the amplitude of oscillation. So damping is used in that. The critical damping is the damping beyond which the free vibration motion will not be oscillatory. So that is critical damping. Damping generally 5% damping is present in the structure. We consider 5% damping. RCC structures in general, and even in steel and masonry structures also. Now in 2016, 5% damping is considered. In fact, earlier steel structures were considering only 2% damping. Now those structures are also having 5% damping now in 2000 as per 2016. Design acceleration spectrum refers to an average smoothen graph of natural frequency or a specific damping ratio for the expected earthquake excitation at the base of single degree of freedom system. that is design acceleration spectrum, which we use in IS 1893. Ductility, it is the capacity of structure to undergo large inelastic deformations without significant loss of strength or stiffness. That is what ductility. Importance factor is determined from design loads for buildings and other structures based on the occupancy category. It is utilized in calculating seismic design loads. The importance factor is a multiplier that increases or decreases the base design load. In fact, in general, importance factor is always higher, more than 1 only. In general buildings, it is 1.0. If the hospital buildings or some important assembly buildings are there, then this importance factor is 1.5. Industrial structures even have 1.75 and 2.0 also. If they have natural hazards or some probability of hazards, so then importance factor is even higher. Natural period of a building is the time taken by it to undergo one complete cycle of oscillation. It is an inherent property of a building controlled by its mass m and stiffness k. These three quantities are related by this equation given in here, 2 pi square root m by k. Response spectrum, it is a plot of the peak or a steady state response, displacement, velocity or acceleration of a series of oscillators of varying natural frequency that are forced into motion by the same base vibration or shock. Response spectrum, which we use in IS 1893, it has three spectrum, so we call it response spectra. They are different for different kinds of soil: hard soil, hard rock, medium rock or medium soil, and then soft soil. So three kind of spectra are given in IS 1893. Its response spectrum is, in fact, we have an x-axis capital T and an y-axis SA over G, spectral acceleration. Peak ground acceleration, maximum ground acceleration that occurred during earthquake shaking at a location, that is peak ground acceleration. This is equal to the amplitude of the largest absolute acceleration recorded on an accelerogram at a site during a particular earthquake. I should tell you that in Bhuj earthquake after 2001, approximately 2.6 G was recorded near Bhuj somewhere, and in Ahmedabad, zone 3.17 G was recorded as peak ground acceleration. Response reduction factor by which the actual base shear force should be reduced to obtain the design lateral force during design-based earthquake, DB shaking. The response reduction factor R is basically depend on overstrength, ductility, and redundancy. So what we do in response reduction factor, we reduce the earthquake force, what is estimated by maximum considered earthquake, and we reduce to the level of design basis earthquake. So we do not design for the largest earthquake, we design for the lower level earthquake and reduce it by or divide it by the response reduction factor, that is R factor, and depends on strength, ductility, and redundancy. In general, if 13920 is considered, IS 13920 data detailing of RCC structure, then spatial moment resisting frame that has 5 as response reduction factor. And if we do not consider, for example, in ordinary moment resisting frame in zone 2, it is not desired, it is not required. So in that case, R factor is 3, and it is different in different cases. P delta effect in structural engineering, P delta effect refers to the abrupt changes in ground shear, overturning moment, and or the axial forces distribution at the base of a sufficiently tall structure. What happens when tall structure is there? It say due to the lateral forces, then axial force is not acting on the centroid. It is eccentric, and because of the eccentricity, P multiplied by E, or that is delta, that moment develops. So we need to design for P delta effect, large deformations. That is what P delta effect. Spatial terminology: center of mass is the point where the entire mass of the floor acts. Mass is majorly contributed by beams and slabs, where stiffness is contributed by the columns and shear walls of the buildings. So stiffness is contributed by columns and shear walls, and mass is contributed by slabs and beams, and also walls. walls also. Center of rigidity is the point where the entire stiffness of the building acts. Stiffness means frame if we are considering as the lateral force resisting system, then center of rigidity is the center of stiffness of those frames. Static eccentricity, distance between center of mass and center of rigidity, that is eccentricity. If eccentricity is there is a chance of, means if there is no eccentricity, symmetric forces will be there, no torsion and eccentricity is there, then torsional effect will occur in the buildings. Diaphragm, a structural element that transmits lateral loads to the vertical resisting elements of a structure. Diaphragms are typically horizontal. Moment resisting frame, it is a rectilinear assembly of beams and columns with the beams rigidly connected to the columns. Ordinary moment resisting frame, which do not satisfy the criteria of IS 13920. A special moment resisting frame, which satisfy the criteria of IS 13920, that is ductility is provided. The special moment resisting frame, RC structural walls, RCC walls detailed and designed as per IS 13920. They will act as lateral force resisting system, means they will resist the earthquake forces. If they are not designed as per IS 13920, they will only resist gravity forces. Weak story, it is one in which the story lateral strength is less than that of story above. So that story will be weak story. Lateral strength is the total strength of all seismic forces resisting elements sharing the total shear in the considered direction. Soft story, it is one in which the story lateral stiffness is less than that of story above. So in weak story, strength is less. In soft story, stiffness is less. Story drift, it is the displacement of one story with respect to the other story. That is relative displacement between two stories. So that is story drift. Soft story, Bhuj earthquake is known for the soft story failure. There were many buildings were having parking and the ground floor. So that floor was in fact soft story. That story was soft story, and many of the buildings were failed in Bhuj earthquake. Earthquake resistant design philosophy. I've told you that maximum considered earthquake. What is maximum considered earthquake? In case of maximum considered earthquake, we call it severe shaking also. So mass of building being designed controls seismic design in addition to the building. Stiffness because earthquake induces inertia forces that are proportional to the building mass. Now, earthquake resistant design philosophy requires that normal buildings should be able to resist minor shaking with no damage to structural and non-structural elements, minor and frequent earthquakes. That is design basis earthquake. Moderate shaking with minor damage to structural elements and some damage to non-structural elements. Moderate shaking is between minor and severe shaking, that is design basis earthquake, and maximum considered earthquake. If some earthquake occurs, then there is a probability or possibility of minor damages. And severe and infrequent shaking with damage to structural elements but with no collapse to save life and property inside adjoining the buildings. So severe earthquake, that is the maximum considered earthquake. If this occurs anytime, then there will be heavy damage to the structural elements, but there should not be collapse in any case. So earthquake resistant design philosophy says that there should not be collapse in case of severe most or maximum considered earthquake. There may be damages in between CB, design basis earthquake, and maximum considered earthquake, but in case of design basis earthquake, there should not be any damage also. And I repeat that design basis earthquake is one earthquake which may repeat or which have return period of 475 years. And maximum considered earthquake is normally it is 2500 years approximately. Equivalent static method analysis. So when the earthquake occurs, it is transferred to the buildings as a response. That acceleration multiplied with mass gives you force, lateral force over the buildings or structure. So how can we design? So there are two methods of designing structures, that is static method or dynamic method. In equivalent static means the phenomena is in fact dynamic, but equivalently find out the static forces and design structure. So concept is a dynamic analysis into partly dynamic and partly static analysis for finding the maximum displacement. It is restricted only to a single mode of vibration of the structure. We can show only single mode. Equivalent static lateral force analysis based on the following assumptions. Assume that structure is rigid. Assume perfect fixity between structure and foundation. During ground motion, every point on the structure experiences same acceleration. Dominant effect of earthquake is equivalent to horizontal force of varying magnitude over the height. Approximately determines the total horizontal force base shear on the structure. What are the limitations of ESM analysis, equivalent static method analysis? In the equivalent static force procedure, empirical relationships are used to specify dynamic and inertial forces as static forces. These empirical formulas do not explicitly account for the dynamic characteristics of the particular structure being designed or analyzed. These formulae were developed to approximately present the dynamic behavior of what are called regular structures, structures which have a reasonably uniform distribution of mass and stiffness. The structures that are classified as irregular violate the assumptions on which the empirical formula is used in the equivalent static force procedure. So in case of irregular structures, we need to consider the dynamic analysis. Equivalent lateral shear force along two orthogonal axes. In fact, earthquake occurs in all three directions, but we design structures in general for two orthogonal directions, horizontal directions. Vertical directions normally is not required because the maximum earthquake which may occur in vertical direction is equal to gravitational acceleration. So in that case, if it is downward direction, we have twice the forces and more than this factor of safety is available in the structure. And if it is upward direction, then it is equal to the acting load. So there is no force in fact. So vertical direction in general is not required in symmetric buildings, but if unsymmetrical buildings are there, irregular buildings are there, cantilever projections are there, tile and roof structures are there, in that case, sometimes we need to consider the vertical acceleration also. The equivalent lateral shear force along two orthogonal axes are considered. And third direction also, IS 1893 says that you need to consider all three directions sometimes. So those combinations are given when to consider vertical acceleration. Design seismic base shear. So while designing these structures, we need to calculate the base shear VB. VB is calculated by AH into W. AH is horizontal seismic coefficient and W is the seismic weight of the building. Horizontal seismic coefficient AH is given by clause 642, that is ZISA by 2R into Z, or Z into Z by 2 into I by R into SA by G. We can split in like this: Z by 2, I by R, SA by G. Z is zone factor, I is importance factor, R is response reduction factor, SA by G is average response acceleration coefficient, corresponds to T, undamped natural period of the structure. In fact, Z zone factor is considered as maximum considered earthquake, divided by 2 is you can consider as design basis earthquake. Importance factor, already we have discussed hospital buildings or important buildings, more than one importance factor is there. So we increase the level of earthquake, then our response reduction factor, that ductility is considered, that then we need to reduce the forces so that the structure is light. But of course, structure will damage and should not have collapse. So to avoid collapse, we need to provide ductility. Zone factor is the indicator of the maximum seismic risk characterized by maximum considered earthquake in the zone in which the structure is located. As per IS 1893 2016, divided in 4 zones 2, 3, 4, and 5. Zone factors are given in table 3. Zone 2.1, 3.16, 4.24, and 5.36. It is like peak ground acceleration. This is as peak ground acceleration 0.36 G in zone 5. I told you that Bhuj earthquake had the level of 0.6 G. So in that way, this value is definitely less. But somehow our procedure is such that which take care of so many things, and the structures designed as per IS 1893 do not fail during earthquake. At least do not collapse. Will not collapse at least during severe most earthquake. Definitely, collapse will be saved. Yeah, damage can take place. This zoning map of India, seismic zone of India. Blue one is 2, about 40%, and then yellow 3, and green 4, and red 5. So you can see what are the different zones from disaster point of view. So Assam, etc., 7 states, and then Bhuj, Gujarat, and few places in Kashmir. They have zone 5, and near to that, zone 4 exists, and then Delhi comes in zone 4, and after that, other few places between zone 2 and 4. There is zone 3, like after 4 in Gujarat somewhere, and near to and Maharashtra also some places, Madhya Pradesh few places. So they are in zone 3, and south Koyana and other things. So they are also zone 3. Average response acceleration coefficient SA by Z depends on the type of rock or soil, height, and also natural period and damping of the structure. So IS 1893 gives you the spectra. Equations are shown here. SA by Z for rocky or hard soil, medium stiff soils, and soft soils. What are the equations? Next slide. Soil type are also defined by IS 1893 in design of, yes. Soil type 1 is rock or hard soil. Soil type 2 is medium or stiff soils. Soil type 3 is soft soils. What is hard rock? Rock or hard soil? Well-graded gravel or well-graded sand, both with less than 5% passing 75 micron sieve fineness. Well-graded gravel sand mixtures with or without fines. Poorly graded sand or clay sand, all having N above 30. So N above 30, stiff to hard clays having N above 30, where N is standard penetration test value. That is considered in rock or hard soil. And medium or soft soil, so 30, between 10 and 30, whatever soil is there. So that is stiff or medium soil, and soft soil less than 10. N is less than 10. States of intermediate compressibility, states of high compressibility, clays, likewise, so they are soft soil. Importance factor, already told you. The important building 1.5. Now there is one residential or commercial buildings other than those listed in 1 with occupancy more than 200%. This is intermediate category, which is now introduced in 2016, that is 1.2, and all other buildings 1.0. Residential buildings in general 1.0, and if residential buildings having occupancy more than 200%, or any commercial building also more than 200%, then that will be, the assembly is there, so it should have 1.2. And important services, community buildings or structures, critical governance buildings, schools, monument buildings, lifeline emergency buildings, hospital buildings, telephone exchange buildings, railway stations, bus stations, metro rail, railways, airports, food storage buildings, fuel station buildings, fire stations, large community, water supply also not mentioned here, water supply buildings, structures. So those structures have 1.5, and if they are in the category of industrial structures, then even higher than 1.5 also. IS 1893 part 4 is there for that. IS 1893 part 4, this part 1. Response reduction factor, it is determined by the type of lateral load resisting system used, the measure of the system's ability to accommodate earthquake loads and absorb energy without collapse. Table 9 of IS 1892 2016. So described table 9. Response reduction factor for building systems, moment frame systems, OMRF 3.0, SMRF 5.0. Likewise, you can see steel buildings also. If they are ordinary brace frames 4.0, special brace frames 4.5, and special brace frames having eccentric braces 5.0. Structural wall systems, unreinforced masonry 1.5, unreinforced masonry designed with horizontal RCC sequence 2.0, unreinforced masonry designed as per 1905 with horizontal RCC sequence and vertical reinforcing bars and 2.5, a reinforced masonry buildings 3.0, confined masonry 3.0. Why I'm telling about masonry? Because even now 80% buildings are masonry buildings. So buildings with ordinary RC structure was 3 and ductile RC structure was 4.0. Flat slab structural system will have only 3.0, and flat slab should have, if flat slab is designed, it should have lateral moment resisting frame also, some system for lateral moment resisting. Next slide is fundamental period. Approximate fundamental period, natural period of vibration is given in IS 1893. Equation is given by which the T is calculated. Different for RC frame building, steel frame building, and buildings maybe steel composite or RC walls or other structures. So 3 equations are there. Earlier there were only 2 equations. Vertical distribution of base shear. So base shear is calculated. BB equal to ASW. Known to you now. How it is distributed over the story. So that is story shear is QI. QI is VB multiplied by WIHI square divided by sigma j equal to 1 to n WJHJ square. So what is WI? Seismic weight of floor I. HI height of floor measured from base. N is number of stories in the building, number of levels at which the master located. So this way, quadratic formula is there by which the story shear is distributed. What also allows is linear distribution also. One wants linear distribution can also be used. Horizontal distribution of base shear is also, this is defined as per FEMA. Horizontal, how it is distributed, horizontal base shear. So horizontal base shear. Next slide, drift story. Story drift. Story drift is a measure of how much one floor or roof level displaces under the lateral force relative to the floor level immediately below. That is story drift. It is a ratio of the difference in deflection between two adjacent floors divided by the height of the story that separates the floor. So drift ratio, story drift is the difference in deflection divided by the story height. There is a tendency for the moment created by equivalent static force acting over the base to overturn the structure. Dead weight of the building is sufficient to raise the overturning force, but it must be checked always. Some considerations while calculation. Percent consideration of imposed load in calculation of seismic weight. Yes. So total earthquake force is not considered for calculating seismic forces, earthquake forces. If live load is superimposed load is up to 3 kN per meter square, only 25% weight is considered, mass is considered for earthquake force calculation. If live load is above 3 kN per meter square category, then 50% of the live load is considered for calculating the earthquake forces. This is because the whole live load may not be there in occupation, and the other thing is it is moving one not fixed. Someplace a fixed imposed load is there, then full load must be considered. And if it is not fixed, then during earthquake it may change the position, and because of changing position, it may act reverse direction also. So it may resist the movement even sometimes. So only 50% life load is considered. Vertical acceleration, vertical earthquake is to be considered when any of conditions satisfy a structure in zone 4 or 5. Zone 4 or 5 suggests that vertical or plan irregularity is there. Then it is to be considered a structure resting on soft soil, bridges, overhang, and long span structure. Vertical acceleration is to be considered. For a structural analysis, for
Satya,
RC and masonry structure, 70% of gross of column and 35% of moment of inertia gross of beam to be considered. Because cracking will take place. So for analysis, it is suggested that 100% moment of inertia should not be considered for stiffness calculation, relative stiffness calculation. So columns, gross of column 70%. So it is assumed that column will crack less, and 35% of gross of beam, because tensile zone will crack totally, or it is resisted by reinforcement only in that. So 35% of gross of beams to be considered. Moment of inertia. For a steel structure, high gross of both beam and column is to be considered. Steel structure we do not reduce in calculating the earthquake forces. Regular and irregular configuration. Failure or weakness of structure starts from discontinuity or regularity. So in fact, they should be avoided. There are two types of irregularities are defined: plan irregularities, vertical irregularities. Two types of irregularities are defined. Maybe due to irregular distribution of their mass, strength, and stiffness along the height of the building. When such buildings are constructed in high seismic zones, the analysis and design becomes more complicated. Vertical irregularities are one of the major regions of failure of structures during earthquakes. Vertical irregularities are mainly of 5 types. Stiffness irregularity. Under stiffness irregularity, the stiffness of the members in a frame are not equal and they vary according to the floor height, modulus of elasticity of concrete moment of inertia of that member. Soft story. Soft story is one in which the lateral stiffness is less than 70% of the story above or less than 80% of the average lateral stiffness of the 3 stories above. Extreme soft story is one in which the lateral stiffness is less than 60% of that in the story above or less than 70% of the average stiffness of the 3 stories above. Vertical geometric irregular. Structure considered to be vertical geometric irregular when the horizontal dimension of the lateral forces resisting system in any story is more than 125% of that in its adjacent story. Mass irregularity shall be considered to exist where the seismic weight of any story is more than 150 of 2% of that of its adjacent story. In plane, discontinuity may be possible. Vertical elements resisting lateral force. In plane, offset of lateral force resisting elements greater than the length of those elements. Discontinuity in capacity weak story. Weak story is one in which story lateral strength is less than 80% of that in the story above. Torsional irregularity is possible. Maximum horizontal displacement of any floor in direction of lateral force of one end is more than 1.5 times its minimum lateral displacement at other end of same floor. The building is said to be irregular. Also, a fundamental torsional mode of oscillation's time period is more than other modes, then two it is said to be irregular. Building with elements like floating and strut column are be prohibited. Also need to overcome or ignore the irregular modes of oscillation in two principal plan dimensions while designing. These are few examples, figures given in figure 3 of IS 1893, definition of irregular buildings, plan irregularity. They are shown here. In next page, figure 4, definition of irregular buildings, vertical irregularities are shown in this figure. Vertical irregularities. Load combinations. When lateral load resisting elements are oriented along two mutually orthogonal horizontal directions, then full design earthquake load in one direction at a time is to be considered. Load combinations are like if we have only dead load, live load, it will be 1.5 times dead load, live load. If it is added with earthquake load and dead load only, then it is 1.5 times dead load, earthquake load. When live load is also included, then 1.2 times dead load, live load, and earthquake. And sometimes, if overturning moment is there, 0.9 times dead load. Stability is a question. So 0.9 times dead load. When dead load is providing stability against overturning, then less there is a probability of less dead load. So 0.9 dead load plus 1.5 earthquake load. This combination is also considered. There are other combinations also when irregularities are there. When lateral load resisting elements are not oriented along two mutually orthogonal horizontal directions, then 0.3 times the other direction earthquake forces are also considered. And in case of 3D, the vertical direction also earthquake is also considered. So three dimensional. These are the combinations in those cases. Irregularities. This was about IS 1893 2016. Now IS 13920 2016 ductile detailing, ductile design and detailing of reinforced concrete structure subjected to seismic forces, code of practice. What is ductility? Ductility of a structure or its members is the capacity to undergo large inelastic deformations without significant loss of strength or stiffness. There should not be loss of strength and stiffness significant. Some loss of strength and stiffness is possible, but without losing its strength, structure is deforming. That is what the ductility. Not lose its strength significantly. Slight losing is allowed. The scope of this code requirements for designing and detailing of members of reinforced concrete structures designed to resist lateral effect of earthquake shaking so as to give them adequate stiffness, strength, and ductility to resist severe earthquake shaking without collapse. So this is important thing. IS 1893 has a design philosophy that in severe most earthquake, maximum considered earthquake structures should not collapse, and RCC structure, if we want to avoid collapse, then this code is must. IS 1320. Provisions of these codes are must. In all lateral load resisting system of RCC structures located in seismic zone 3, 4, and 5, these provisions are mandatory. Optional in zone 2. To monolithic RC construction, not for precast RC structures. Precast RC structures, these provisions are to be should be there, but in special there should be some special provisions also in precast. So that is why it is said that these provisions are not for precast RC structure. Means some more provisions may be required because of that. Otherwise, these provisions are to be followed in precast also, but additional should also be required. Additional would also be required in joints and other things. Because in RCC structures, monolithic construction is there. So if these provisions are there, monolithic construction will give good resistance. In precast, there are jointed connections. So in jointed connections, even though you are providing these, but joints are weak, and it will be difficult to avoid collapse. So that is why for precast structures, special provisions may be required. Flat slab structures must have a LFRS capable of providing similar level of performance as envisioned in this standard and be compatible for drift. So lateral force resisting system should be there in flat slab structure. General specifications, design construction of RC frame buildings as per IS 456, except for the elements participating in LFRS, lateral force resisting system. Minimum concrete grade M20, but M25 for a more than 15-meter height in seismic zones 3, 4, and 5, and not less than as required by IS 456 based on exposure conditions. In any case, IS 456 has to be followed. In addition, there are provisions in addition to IS 456, they need to be followed in 1320. The steel reinforcement less than Fe 415 can also be Fe 500 and Fe 550 having elongation means suggested in 1320 as less as possible, but 415, 500 and 550 they are also allowed. Condition is elongation should be more than 14.5%. Low grade of concrete and high grade of steel reduce ductility. That is why less than M20 is not used, and in more than 15-meter high buildings, M25 is recommended, and high grade of steel reduce ductility. But if it is giving 14.5% ductility, that is recommended. 0.24% proof strength of steel bars on tensile test should not be more than 20%, and it is also recommended that it should not be more than 20%. Ultimate strength 2.2% proof strength ratio shall be at least 1.15, minimum 15% ultimate strength. Lintel beams shall preferably not be integrated into columns to avoid short column effect. If integrated, they should be modeled in structure analysis, similar plinth and staircase beams also. So if they are integrated, they should be modeled in the analysis. If you do not model and provide it on site, there is a possibility of short column effect. What is short column effect? Short column effect is you are designing a long column and providing a short column, then the column stiffness becomes higher and it attracts more force, and then the distribution disturbs, and while it is not designed for that force, the column may fail. Irregularity should be avoided. Leaning columns and setback columns should also be avoided. Performance of buildings in such cases is poor during earthquake shaking, so that is why they should be avoided. In case of any such irregularities, nonlinear analysis shall be performed to demonstrate that there is no threat to loss of life and property. What are the provisions in beams, in flexure, beams resisting earthquake induced effect in which the factored axial compressive stress does not exceed 0.08 FPK. So what do we define as beam? Axial compressive stress is less than 0.08 FPK, then that is beam. If beams with factored axial stress more than 0.08 FPK, they shall be designed as per requirements of columns also. So in beams, if factored axial stress is more than 0.08 FPK, then you need to consider the provisions of columns also. Otherwise, if it is less than that, it's okay. For beam provisions will be there. What are the criterion for determining minimum tension reinforcement? As in IS 456/1978, there are some references by which minimum criteria for determining minimum tension reinforcement are given. Next slide, beams. Preferably width to depth ratio more than 0.3. Next slide, yes. So width to depth ratio should be more than 0.3. Width not less than 200 mm in any case. Beam width. Depth D not more than 1/4 of clear span. Width of beam VW web shall not exceed width of supporting member C2 plus distance on either side of supporting member equal to the smaller of width C2 in 0.75 width. Restrictions on member sizes. Ductility provisions are valid only for members of usual proportions. Restriction is due to the reason that ductility provisions are valid only for members of usual proportions. If abnormal proportions are there, ductility will not be achieved. Longitudinal reinforcement, at least two 12 mm diameter bars, each at the top and bottom. Minimum 2 bars of 12 mm dia at each at the top and bottom. So minimum 4 bars. Rho minimum, that is minimum reinforcement, 0.24 square root of CK upon Fy. Maximum longitudinal steel ratio on any face of any section to avoid congestion. Rho maximum, that is 0.025, that is 2.5% steel is the maximum which should be provided in the beams. Longitudinal steel on bottom face, at least half that on top face.
Huh?
At any section on top or bottom, at least 1/4. This clause is very important. 6.2.3. Bottom face at least half. Near support. Near support. What is the top steel provided? Bottom, bottom, minimum half of that should be there. At any section, top and bottom, at least 1/4 of top reinforcement and near support. At an exterior joint, top and bottom four face bars shall have anchored length LD plus 10 times bar diameters, allowance for 90-degree band between minus. So when the joint is there, exterior joint, top bar will continue to development length from face of the column. Development length plus 10 times bar diameter. Yes, you can reduce 90-degree allowance for 90-degree band. Similarly, bottom bar also. Next year. Splicing of longitudinal bars, lap splices, mechanical couplers, threaded splices are allowed. Lap splices should be provided where the yielding will not occur, that is in zones other than 2 times the effective depth from supports. In between somewhere it can be provided. Mechanical couplers are suggested. Welded splices should be avoided, but ductile weld can be used. Not more than 50% bar should be spliced at any section. Why 50% in the bottom was required? 50% of reinforcement in the bottom was required because of reversal of moment during seismic shaking. Moment may be in opposite direction, and this earthquake force may come from both directions, to and fro. That is why, and gravity load only top is in tension, but when say to right, you can see one bottom, left bottom is in tension, straight to left, right bottom is in tension. So that is why bottom should also have near support. Some reinforcement should have. Next slide. Steel at top and bottom face should be at least 25% of maximum negative moment steel. Anywhere 1/4, we have already seen that. The figure how anchorage of beam bars in an external joint, column face to LD plus 10 times bar diameter. And so the bottom also and top bars also, both the bars. LD is development length in tension, DB is bar diameter. This was the condition of splicing. The hoops are provided over the entire splice length at a spacing not exceeding 150 mm. Left length shall not be less than the bar development length in tension. Left splices shall not be provided within a joint within the distance of 2D from joint face and within a quarter length of member where flexure yielding generally occurs. 50% of the bar shall be spliced at one section. Next slide. What we have discussed from here. Longitudinal bar splices. Next slide.
Yes, sir.
Next slide. Longitudinal bar splices. Hoops required over entire splice length, not more than 150 mm center. Left length should be greater than or equal to development length and tension. Left splice is not to be provided within a joint within a distance of 2D from joint face within a quarter length of member where yielding may occur due to seismic forces. Left splices are not reliable under cyclic and elastic deformations. Should be avoided. Wider splices and mechanical connections may also be made. However, not more than half the reinforcement shall be spliced at a section where flexure yielding may take place. Location of splices shall be given by 6 to 6. Beams continued. Next slide.
Yes, sir.
Transverse reinforcement. Only vertical links, 135-degree hook, 6 times. This is amended, in fact. 135-degree hook should have 75 mm or 8 times bar diameter. 6 dB was written there, so it is amended. 90-degree hook on one side is allowed. Minimum dia 8 mm, shear force capacity of a beam. Next slide. Sometimes there is a difficulty in having a stirrup in beam. Then this U stirrup and cross tie in figure B, it can be done like this. So it can be provided. It will help in placing the reinforcement at the side. We have reinforcement of vertical hooks, 135-degree hook with 10 times diameter, greater than 75 mm extension. Next slide. Shear force is to be resisted by vertical hook shall be the maximum of calculated factor shear force as per analysis, and shear force due to formation of plastic hinges at both the ends of the beam plus factor of gravity load from the span. Slide आगे कीजिए अमित.
Yes, sir. It is not changing, sir. I have changed from my side.
Okay. Yes. Okay. This is okay.
Yes.
These are the equations. How to calculate shear force on the joints. Here, let me tell you, not mathematically, just physically, what is happening. Shear capacity of beam should be higher than the flexural capacity of beam, so that brittle failure does not occur. So what do we do? Design shear force. We add the shear force when yielding will take place. Maximum capacity will be utilized. Beam's maximum capacity is utilized at that time. Moments will be mu limiting moments. So mu limiting moments at both the ends divided by length will give you the shear force, which will be the maximum during yield. And mu limiting has got factor of safety 1.4, so you multiply in that 1.4, and this is added in the design load, and that much shear should have the shear capacity of that particular joint. So this was the concept behind these equations. So shear capacity will be higher than the flexural capacity. Shear beam will not fail in shear before flexure. Capacity design concept to ensure shear failure does not occur prior to flexure failure. Detailed discussion is given in this paper in concrete journal. Building example. What is there in this? Beam should fail first, but not column. Column should fail first, but not beam column joint. And beam column joints can fail, but not foundation. So failure sequence is slabs first, then beams, then columns, then beam column joints, and then foundation, and then soil. This is what the sequence of failure. If soil fails first, the whole structure will collapse. Suppose soil is okay, foundation fails, then also structure will collapse. The foundation has to be strong than structure. This is what the capacity design concept is given by Park and Foley, New Zealand. Foundation is not failing, but if beam column joint is failing and beam columns are not failing, then too the structure may collapse. So that's what the sequence. And suppose beam column joints is okay, column is failing, beam slabs is not failing, then slab beam will uh, will collapse and will get down, and then due to impact the whole structure will collapse. So sequence of failure should be slab beam column joint, foundation, and pile. This is of the how the shear force is distributed. Base shear is distributed. Maximum is at top and minimum is at bottom. And hinges, so beams, plastic hinges are formed. And of course, lower story column hinges will be found. That's okay. But column is strong enough. There's one concept of shear, design of shear, which is that equations they are taking from this example. So moments, top and bottom moments carrying capacity m omega. One you can see from bottom and other is top because earthquake covers from one side only. So bottom reinforcement bar will calculate mu limiting, and the other hand, other end top bars will give you mu limiting. So both are added, and then divide by L will give you V shear force. So that has added in the design shear force, and more than that, shear capacity will be kept. Next.
Yes, sir.
What happens when confined reinforcement is there or unconfined reinforcement is there? Unconfined means IS 456 detailing, that is unconfined, and 13920 detailing is confined. So you can see a stress strain curve. Unconfined is little value, confined is having larger value. So ductility is there. So confined is suggested in IS 13920. That is the reason. So that ductility is present in RCC structure. Over strength moment hinge properties. M theta curve building example. So this simple graph. Continue next. Shear design concept is only explained here again. Next. 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 Same thing. Saying repetitive slides are there. Yes. Hoop spacing over 2D length of either end of beam not to exceed. This is a special confinement, a special confining reinforcement. So in this diagram you can see up to 2D of length from supports, hoop spacing should not exceed d by 4 or 8 times the diameter of a smallest longitudinal bar, but need not be less than 100 mm. Hoops at above spacing also over 2D on either side of beam where structural yielding due to seismic faults may occur. Elsewhere, spacing of vertical hoops less than or equal to d by 2. So you can see up to 2D both sides, hoop spacing less than or equal to d by 4 or, and 8 dB, and in between not greater than d by 2. So near to support, hoop spacing is less for confined concrete. We have ductility over here. So this is special confinement reinforcement of beam. Next. Columns and inclined members. Columns and inclined members resisting earthquake induced effect in which, so first it is the definition of columns. If axial compressive stress due to gravity and earthquake effect exceeds 0.08 FCK, those members are called as columns. Columns other than rectangular and circular shapes will be designed using specialist literature. Here, rectangular and circular detailing is given. Minimum dimension shall not be less than 20 times the bar diameter. GB is the larger diameter of the longitudinal bar in the beam joining or 300 mm. You can see minimum dimension is 300 mm. At the same time, if beam joining column is having 20 dia bars, 20 mm bars, then the minimum dimension of column should be 20 into 20, that is 400 mm. And if it is 25 mm bar is there, then the minimum dimension is 500 mm. Imagine. So those 200 columns are not now suggested by IS 130. They are restricted. 200 columns are not allowed by 13920 now. Minimum is 300 mm, and even more dimension is required if beams are having larger diameter bars. Cross section aspect ratio not less than 0.45. B by D ratio not less than 0.45. Vertical members having cross section aspect ratio less than 0.4 shall be designed as a wall. This is amended probably. It is instead of shortest cross section dimension to the perpendicular dimension shall be not less than 0.4. Instead of 0.45, it is again 0.4 only, I think. So, for example, 200 by 500, 200 column is not allowed. In fact, 300 by 700 column is okay, but 300 by 800 columns will not be allowed. So, one other dimension, the other dimension is 800, then 300 will not be allowed. Okay. Relative strength of beams and columns are design, capacity design concept. Sum of nominal strength of column equal to 1.4 times the sum of nominal design strength of beam. You have seen these in case of shear capacity design concept was applied. Now in case of columns also, capacity design concept has to be applied. What is this concept? In beams, it was that shear generated by limiting moment capacity should be added in design shear, and total shear capacity should be higher than that. Now in columns, capacity of columns, for example, shear capacity of columns is also calculated, and it is checked that shear capacity of column is more than the shear capacity at joint. At the same time, flexural capacity, that is in bending, flexural capacity of column or bending moment capacity of column should be more than the bending capacity of beams. So this concept is introduced in IS 13920 2016. It was not earlier there. So now this concept is applied. So columns should be stronger in capacity than beam. If this should look stronger is not like that. 400 by 600 column and 400 by 800 beam is okay. But 400 by 600 column should have a capacity in moment carrying capacity higher than 400 by 800 beam. So capacity is checked. That is called nominal strength of columns. 2.4 times the nominal design strength of beams. If less, then the column shall be considered to be gravity columns only and cannot be considered as a part of lateral load resistance system. If this capacity is less, they will not be considered as part of lateral load resisting system. Moment of resistance of beam is calculated as per IS 456, and columns, as in case of beams, corresponding to zero axial force on the design beam interaction diagram. It was written there, but it is again amendment is there. So capacity of beam and column is calculated as per IS 456 in general, you can say. Check shall be performed at each joint for both positive and negative directions. This check shall be waived at roof level only in buildings more than 4 story tall, because in roof, otherwise there are only, means if corner we consider only one beam and one column, and very huge column will be required at roof in that case. So it is relaxed in this. Okay, what will happen in that case if it is relaxed? column will form a hinge there. The column will crack before beam cracks, but will not collapse in any case. You not to worry. But okay, so column will crack first and beam will rest on that. So in structure as a whole in earthquake will not collapse. These provisions are not applicable for the flat slab structures. Flat slab structures, a very defined lateral force resisting system is required. Circular column shall have minimum of 6 bars.
चल रहा है सर सर
Splicing of longitudinal bars,
15
lap
मिनट में
splices similar to beams, lap splices similar to beams, and spacing of links less than 100 mm. In beams it was defined at 150 mm, but in columns in less than links less than 100 mm. Only in central half of clear column height and not within a joint or within a distance 2D similar to beam from face of the beam. Not more than 50% of bars to be spliced at any one section. Lab splices only up to 32 mm diameter. Mechanical splices are for bars above 32 mm. If longitudinal bars are more than 32 mm diameter, then mechanical splices are suggested, recommended, and not the lab splices. Mechanical coupler should exhibit same properties as desired for ductility in yielding zone. Welded splices not allowed in yielding zone. Not more than 50% bars shall be spliced. Welding of links, ties, etc. is not permitted in any seismic zone. Column that extends more than 100 mm beyond. So this is confined core owing to architectural requirements will be detailed. Next, this diagram is explaining that. Transverse reinforcement. Next slide. Closed links with 135-degree hook and 8D length, but not less than 60 mm. Again, this is amended. Last slide. Actually, Ali said this.
yes
Yes. So again, this is amended. 8 times bar diameter and 75 mm. Closed links with 135-degree hook, similar to beams. Minimum dia 8 mm for long bar, up to 32 mm, 10 mm if more than 32 mm. Maximum spacing of legs 300 mm. Cross tie required when more than 300 mm. Hither. Maximum spacing of links half the least side of the column except where spatial confining reinforcement is required. These are the few clauses which you have to consider for the spacing of links. Transverse reinforcement, the same thing. Here it is written correctly. Earlier code was having 135-degree hook, 10 times diameter or 75 mm. The same thing is there in amended 2016 also. Yes, this is the diagram for that. Next. Next. Same thing explaining in diagram what we have just discussed. Next. Next. Continue. Design shear force in column 13920-2016. This was earlier also in 1993 also, same thing. Similar to beam, 1.4 times MU limiting at one end and MU limiting at the other end divided by height, story height. So this is the shear force in column. General in IS 456, columns are not designed for shear force. Simple ties spacing are specified and those are to be provided in IS 456. What that's for IS 1920. This calculation is required and check is required. Next. Design shear higher of shear force as per analysis. Same thing. What is the equation in last slide? Same thing. Next. Diagrammatically. Same thing. Special confining reinforcement. In columns also, special confining reinforcement is required. This requirement shall be met in beams and columns unless larger amount of shear reinforcement is required from shear consideration. Here, same things are not for beam. There is a difference. It is mainly for columns. It was written in beams, but now beams, all the things are not required for beams. Beams are separately already explained, so those will be for beams, and these are for columns. A special confining reinforcement in the form of closely spaced hooks or spiral to confine concrete in the vulnerable regions shall be provided for ductile behavior of concrete, provided over length of L0 from face to the joint where L0 not less than larger lateral dimension of the member 1/6 of clear span and 450 mm. Have a spacing not more than 1/4 minimum member dimension of the beam or column, 6 times diameter of the smallest longitudinal bar or 100 mm length. So these we have to check, not more than this spacing. Area, these calculations we have to check. Area of troughs in circular links and rectangular links should follow this formula. You have to check by this formula. This is the figure, next slide, of confining reinforcement. Here L0 is explained here, near to beams at top and bottom for L0. In between the spacing may be more. Near to junction, the spacing are close, that's the spacing. And even confinement joints with beams framing into all four sides confining reinforcement. And joint reinforcement as per clause 8.1. So when the beam confining is only on one side, you need to continue same reinforcement, confining reinforcement to joints also. And when from all four sides, joint is confining, column is confining at joint, then you can reduce to some extent that spacing. Same formula which we have already seen. Here is one example. Next slide. How to calculate. For that. Right.
खत्म होने वाला।
Continue. Next. Same thing. Next. Next. Yes. Here you can see in footing what should be there. At least 300 mm. Special confining reinforcement in the footing should be continued into footing or mat. Over full height, a point of counterflexure not within middle half of member. Somewhere it may be needed for the full height in different cases. A special confining reinforcement shall be provided over the full height of column which has a significant variation in stiffness along its height. This variation in stiffness may result due to abrupt changes in cross-section size or unintended restraint to the column provided by stair slab, mezzanine floor, plinth or lintel, beams and framing into column, RC wall or masonry wall adjoining column and extending only for partial column height. Next. Next. This is one example of that. Next. Continue. Same thing. Example. Next. Yes. Yes. Interior column design of an RC frame building, Seismic zone 5. Here one column is designed. Numerical example is given to calculate how to calculate forces. Then continue this. We'll skip this. Yes. There is one more example, ductile retaining for columns. Then beam column joints. Next slide. Yes. Beam column joints for moment resisting frames. Design of beam column joint for distortion shear. Shear strength of concrete in a joint. Nominal shear strength tau JC of concrete in a beam column joint shall be like these criteria we have to satisfy. For beam column joints also. This check we have to apply in beam column joints. Yes. Next. Transverse reinforcement. Confinement reinforcement in joints when all four surfaces are framing at least 75% width. That is called confinement. We have already discussed this. Skip those slides. Example problems. Yes. Requirements of this section apply to special shear walls. Now these are the provisions for shear walls. We'll quickly go through in 1 minute. Minimum thickness shall not be less than 150 mm and 300 mm for buildings with coupled shear wall and seismic zone. Minimum thickness must conform to IS456 for fire resistance in any case. Thickness greater than 150 mm. Thinner walls have a tendency to buckle out of plane. Minimum ratio of length of wall to its thickness shall be 4. There are walls, squat walls, intermediate walls, slender walls. Then there are equations of medium reinforcement in different walls, squat walls, intermediate walls, and slender walls. And there are formulas. Yes, in this slide, table 1, minimum reinforcement RC shear walls are given. And equations for designing shear walls are given in IS 13920. Design for axial force and bending moments, they are given. So moment in annexure of IS 13920, equations are given. We need to calculate boundary elements in shear walls. And I will skip all these slides now in shear walls, considering this as advanced topic. And time is also not permitting me to continue this. So thank you at this moment. Amit, if anybody wants to ask some questions.
Yes, sir.
Ready to reply.
Please ask your questions. Actually, sir, someone has written that it is very tough to understand all these things, but we will try to understand if we share them the video. We will share with them the videos also.
Yes,
Sir.
video and PPT, both the things will be given to them, no problem.
You can also mail us the questions so that
Yes.
we can send to sir, and once we get the response from sir, we will revert back you the answers.
Yeah, definitely. You can share my email ID rakeshkare@hotmail.com
Yes.
and WhatsApp number 942505348. I don't mind if someone wants to ask any question. I'm ready to answer.
I have shared, sir.
Okay.
Yes, sir. So, sir, should we end the session, sir?
Yes, thank you.
Yes, sir. Thank you very much, sir. Thanks a lot, sir.
Thank you, Amit.
So right now we are leaving now, and we will come back again at 3 p.m.